Okay, right, this is a relatively short bit, and then we're going to have a look at some questions and start getting used to answering questions and working things out and you know, taking different angles on stuff. But I just want to go through fairly quickly now a couple of examples of control systems that involve hormones, and going to do the control of blood glucose in a very, very simplistic way. So if you choose to do this for an assignment, you will need a lot more detail. You'll need to talk about insulin receptors and glucose transporter channels and all that sort of thing as well. But I'm going to do that one, and I'm going to do the antidiuretic hormone one, which is to do with osmoregulation. So we start off with first example then is going to be glucose regulation, and I'm going to use this full board panel to draw a flow chart for this. Oops. Right, so glucose regulation. Now, obviously there is a normal for glucose levels in the blood, or glucose concentration, we should say, not levels really. And it's a range, it's a narrow range, and it's usually measured, well, millimoles per litre is the common measurement. And anywhere between about 4 and 8 is fairly normal. And after meals, it'll go up. Obviously, before meals, you know, it's been used, it'll go down a bit, but it shouldn't really fluctuate either side of those. And the problem is, when blood glucose levels go up, what do you do with it? You know, if you can't, well, you need to store it if there's too much. Otherwise, it gets filtered out by the kidneys. There's a sort of threshold, you know, that the blood will accept, and then it gets taken out by the kidneys. And that takes glucose out of the body that's then not there to use, and so storing it is the ideal option. Now, one way we can store glucose is turn it into fat. And actually, that's one of the things that insulin does. It helps the body create fat from glucose. But the other thing it does is convert it into glycogen. Now, glycogen is useful because it's not soluble. Glycogen is long chains of glucose molecules joined together into what we call a polymer. So lots and lots of glucose joined together, not soluble anymore. And of course, if it's not soluble, it won't affect the water potential of the body cells, and it can't just be washed out with water movements in the body. So glycogen is a storage carbohydrate in the human body, animals generally. And of course, then when you want glucose released, you can just break down the glycogen. Now, there are words in this that all sound very similar but are very different. So making glycogen, the process is glycogenesis. Breaking glycogen down back into glucose is glycogenolysis. We've got glycogen is the storage substance. There's a hormone called glucagon. And then we also get glucose added to the blood by a process in the liver called gluconeogenesis, which makes new glucose from other things. So it does get a bit complicated. If you're going to do this one for the assignment, you need to be clear about all those different steps. I'm going to keep it really simple. But if we start, I'm going to go up and down from my starting point. If we start with normal blood glucose here, then it may go up, it may go down. If it goes up, and in here I will just put an up arrow to say raised blood glucose. That's detected by cells in the pancreas. Now, part of the pancreas produces hormones, and part of it produces enzymes for digestion. The part that produces hormones is divided up into little patches called islets, that's little islands, and they're called the islets of Langerhans. And there are two sorts of cells in there, alpha cells and beta cells, and it's the beta cells in the islets of Langerhans that produce insulin. So the effect of raised blood glucose is beta cells in the islets, which is spelled like that, of Langerhans. And that's in the pancreas. I'm not going to put that in because I haven't really got room. No, I've put the H in the wrong place. Langerhans. So in islets of Langerhans, release insulin. All right, so that's in the pancreas. And then I've got a box around it. And what insulin does, it does bind to receptors on cells, opens glucose channels, but that means that it increases glucose uptake. I could have used an up arrow for that. Increased glucose uptake by cells generally, and increased use as well. So increase glucose uptake and use by cells, any cells you like. Then conversion of glucose to glycogen. And then conversion of glucose to fat. And all of those things will reduce the blood glucose and take it back to normal. I've hardly left myself enough space there. But the effect here then is that we get reduced blood glucose. And that takes us back to normal. So in somebody who doesn't produce glucose, insulin, and that would be type 1 diabetes, they don't make insulin because they've not got the beta cells because the body's destroyed them. In type 1 diabetes, it's an autoimmune disease, and the body actually destroys its own tissues. There are several other autoimmune diseases, things like, I think, multiple sclerosis is an autoimmune disease. Off the top of my head, I've now forgotten all the other examples. But the body will attack itself. Rheumatoid arthritis is also autoimmune. And the body's immune cells just go wrong, basically. And, yeah, sometimes there are triggers. And with diabetes, type 1 diabetes, they think there might be an infection that children often encounter in early life that actually triggers this malfunction of the immune system. But there are quite a number of autoimmune diseases where the body attacks itself. Another one is, vitiligo, where you get white patches in the skin, and the body destroys its melanin-producing cells, autoimmune. And so it's quite strange that. No insulin, so when there's sugar in the blood, it can't be taken up, it can't be converted to it can't be converted to glycogen, it can't be converted to fat, so there's no storage. So there's real issues, with low blood sugar or hypoglycemia being a real risk there. With type 2 diabetes, usually producing plenty of insulin, but the cells in the body lose their sensitivity to it. So you can't give somebody with type 2 insulin, not early on, won't have any effect. They're making insulin anyway. The medication for type 2 is drugs that will actually enable the cells to take up glucose other ways and stop the liver from making glucose as well. Metformin's the one, yeah. So that's how the body will normally respond to high blood glucose. If we've got low blood glucose, whoops, I was going to write low again, then obviously we need to try and raise the levels. And this time we've got a different set of cells in the pancreas. This time it's the alpha cells. Oops, no trouble spelling. Langerhans. They release the hormone glucagon. Now, problem with that is, of course, it sounds very similar to glycogen. glucagon ending in ON is the hormone. So remember, hormone ends in ONE and glucagon is ON. And that doesn't reverse all of this. It doesn't break down fat. It doesn't make the cells spit out glucose exactly, but it does convert the glycogen back to glucose. And so that, oops, I'm going to have to go up there, will raise the blood glucose. And that will take you back to normal. So we've got two different correction mechanisms going on here. If you think about, when we're talking about homeostasis generally, talking about monitoring, the body will monitor conditions. It will then kick off the right correction mechanisms. And when it gets back to normal, those get switched off. So what we've got here are two different correction mechanisms for deviations either side of normal blood glucose. So if blood glucose goes up, we get insulin, which takes glucose out of the blood and stores it. And if blood glucose goes down, we get glucagon, which releases glucose back into the blood. Right? So between these two, we've got a balancing act going on. Phrase I didn't include with the homeostasis bit yesterday, I don't think, was dynamic equilibrium. That's a really good way of saying what homeostasis is. It goes up and it goes down. It's constantly on the move, but it's balanced overall. So you get this dynamic equilibrium as a sort of consequence of having these two systems switching on and off. So what we've got in terms of the sort of overview here is, here's glucose as a whole bunch of individual little sugar molecules. We can convert that into glycogen, which is sugar molecules joined together. And that is under the control of insulin. So of course you can go back the other way. So you can go back from glycogen to glucose under the control of glucagon. Right. Unfortunately similar words, but yeah. Useful words. I mean, going that way, the insulin process across there, you've got glycogenesis. That's the left to right, that bit. And then glycogenolysis goes the other way. Right, so I'll put left to right, and then right to left for that. Okay, so it's a bit like, theoretically, having an air conditioning system, which I couldn't get through to reception to get it turned off, but where you've got a heating circuit and a cooling circuit. So, if the temperature in the room goes up, you turn the cooling circuit on. If the temperature goes down, you turn the heating circuit on. And so we've got two different systems here to control blood glucose levels. With the other example that I want to tuck in quickly, with antidiuretic hormone, this is a single system that we either switch on or off. All right. Now, Antidiuretic hormone is involved in osmoregulation, which is controlling water levels in the body. And its name tells you a little bit about what it does. A diuretic increases urine production. So you can take tablets that will increase urine production, and they're, people call them water tablets, but they're diuretics. So antidiuretic reduces urine production and hangs on to water in the body. And so this all happens in the kidney, and it's by changing the number of aquaporins in the kidney tubes. But we're just going to look overall at how the hormone gets involved at this level, and then we'll be back to it later on. So this is EG2, osmoregulation. The hormone is known by several names. ADH, antidiuretic hormone. Also known as, AKA, vasopressin. Now, vasopressin, the word, vaso means vessel and pressin means pressure. So this is because it affects blood pressure. And it's because it changes the amount of water in the blood. So the more water's in your blood, the higher your blood pressure. The less water in your blood, the lower your blood pressure. So this hormone does actually have a role to play in blood pressure control. So if you choose to do the blood pressure assignment, then you'll need to mention this hormone, because by losing water from the body, you can lower blood pressure. Now with this one, what we're having to detect is the water potential of the blood. So I'm going to do the same sort of thing with this. Use a whole odd panel for it. Where did that go? Right, okay. And if we start over here this time with normal blood water potential, then the water potential will go up if the body loses water, won't it? And the blood gets... No, it won't. Sorry. The water potential will go up nearer zero if the body gains water. It's the problem, isn't it? The ups and downs and the negatives and... Right. Increased water potential is nearer zero, so that's more dilute. So increased water potential. Let's put here blood more dilute. We can afford to get rid of water in that situation. So we don't want an antidiuretic effect. So I'm going to need to just scroll that down a little way, because the one that we actually want the ADH for is down here. If we've got a lower water potential, right, if it goes down, that means that the blood is more concentrated. Oops, blood more concentrated. Yes. Yeah. It is. Yeah. More negative is lower, and more negative is more concentrated. You have to stop and think about it, don't you? This is a situation where we want the body to reduce its water loss. So this is where we get ADH from the pituitary gland. So I'm just going to put ADH released. And up here we've got ADH not released. Keep it simple like that. Oops. What we want to do is look at what ADH does. Well, it stops the kidneys actually allowing water to leave the body. So it takes water back into the blood. So more water is taken back out of potential urine into the blood. So increased water reabsorbed, we'll say, because the kidneys potentially will filter all the water out of your blood. So if we get more water going back into the blood will become more dilute, it will raise its water potential and will go back to normal. And what you get here is small amounts of concentrated urine as a result. So that's like what happens in the summer sometimes. You know, you go all day without going to the loo and suddenly realise, and then it's, you know, like golden syrup sort of thing. And then, you know, you suddenly get a cold day and it goes the other way and you can be piddling for England, you know. If we haven't got ADH, we've got our normal diuretic effect. So we actually get increased water lost from blood into urine. So you get larger amounts of dilute urine. But we will talk about the actual processes involved there and the role of aquaporins when we get round to the kidney. And so we will. This is an introduction to what ADH is doing, and we'll come to the actual mechanism. And it is an important bit because it will actually be part of the exam. So both of these will. Well, what will this do? We're losing water here. So we've got. Let's get this the right way round. We've got a lower water potential of blood as a result. Right, blood's getting a bit more concentrated this way and it takes us back to normal. And this one, I always find this really hard to do. We get the increased water potential of the blood as a result of hanging on to more water. It makes it more dilute, so the water potential rises, and again we're back to normal. But my reason for putting this one in is really just to show you that this is one system, and it's switch it on, switch it off, switch it on, switch it off. Okay, so you've got sort of two contrasting control systems there. Now both of these have a role to play in the assignment. So the glucose to glycogen controlled by insulin and glucagon would be a component of the blood glucose assignment, not surprisingly, and this would be a component of the blood pressure assignment, because the amount of water in the blood, it'll change the volume of the blood, and therefore the more water in your blood, the higher your blood pressure, the less water in your blood, the lower your blood pressure. And so ADH, this is why it has that name, vasopressin as an option, can actually help to control blood pressure. It tends to raise blood pressure, if you think about it, all right? If ADH is released, then it's going to cause blood to take up more water, or to, you know, water to be retained in the blood. And so ADH will actually increase blood pressure. Okay. Now, with the glucose one, of course, you're familiar with diabetes as a malfunction of that, and the two types. But the full name for that sort of diabetes is diabetes mellitus. The mellitus bit comes from the Greek for honey, mele. And that's because the word diabetes actually means passing across or passing through. Dia, like diameter across a circle, dia. So it means passing across, and it means passing out into the urine, and it means sweetness passing out into the urine. Okay, so how did they originally test for diabetes? Test the urine for sweetness. Yeah. Of course, tests are a little more sophisticated these days, but yeah, that was an option. There is a form of diabetes also associated with ADH, and it's called diabetes insipidus. Now, insipid means weak and wishy-washy, very dilute. So this means a lot of water passing across into the kidney, into the urine, because if you've not got ADH, then the body will keep losing water, won't it? That top loop. And the problem for people who've got diabetes insipidus is they could dehydrate very quickly. So they need to keep drinking, but they can also take ADH as a medication to actually help to control their water levels. But yeah, if you come across another diabetes, then that's the one that's associated with ADH. Okay, I'm going to stop the content at that point then and direct you to the handout folder. And you've got several things in there. You've got a sheet that says homeostasis check questions, which if you just feel like doing those, you can. There's a sheet which goes with a set of dominoes, which has got some questions on that I haven't necessarily covered, but you can always guess. And then there are a few bits of A-level questions, which may be a little bit much at the moment. We will come back to those. I think, you know, given how few people we've got in here at the moment, I don't want to go through those questions today. But have a look either at the check questions or probably what you would prefer is the dominoes. But yes, I shall stop at that point.